There are many, yeah, if you actually see any of the textbooks, especially the foreign authors, Incorporated Bit or Angel or Holman, etc., there are many practical problems. Okay? The exercise problems are also good. Once you actually practice these exercise problems, you will get a good feel for problems also. Okay, so whatever given in the exercise problems, they are all very good. You can actually select, choose some questions, and then you can actually try to solve it. The questions which were actually sent it to you, they were actually taken from improper and debitor. Uh, okay. So those who want to take the notes and all, you can actually take it. Okay. Anyway, I'm actually not going to record this lecture because this is just tutorial and there is actually nothing on this. Okay. Uh, yeah. Okay. So any of you actually gone through the questions? Anyone of you actually tried? Yeah. Very good. Yeah. So it seems like only one who is actually taking the effort is actually me only. Anyway. Uh, yeah. So without practicing the problems, you will not get the better understanding of the theories. Okay. So even though you understand, you actually feel like you actually understand the theories and all, but when you actually start solving the problems, especially for heat transfer uh, and fluid mechanics still not that this much problems. So especially for this heat transfer and thermodynamics, so there are actually very tricky ways in which questions can be actually asked. Okay. So when you actually start to solve these problems, then you can actually see how the physics actually comes out. And okay. So long as you are not practicing the problems, you will not be actually able to answer this, or you will not be able to really appreciate the equations whatever we actually solved. Okay. The first question says a square silicon chip. Okay, so here the chip is actually shown, a square silicon chip, and the activity is actually giving is of width 5 mm on one side, width 5 mm on one side, and thickness t of 1 mm. Okay, so we will actually get the cross sectional area as well as some thickness, something is actually there. The chip is mounted on a substrate such that chip's side and back surfaces are actually insulated. So if you see the figure, you can actually see that it's one side is actually fixed on the substrate. This is actually the substrate. Can you all see the screen?
Yes, sir, we can see the
Yeah.
screen.
Yes, sir.
You can see this mouse also moving, right? Cursor also moving.
Yes, sir.
Yeah. Uh, yeah. While the front surface is actually exposed, so the side surfaces as well as the back surface, everything is actually insulated. These dotted lines, they are all insulated. Okay, while the front surface is actually exposed to the coolant. So the top surface, okay, that we can actually see. So that is actually exposed to the coolant. So if 4 watt are actually being dissipated in the circuit mounted on the back of the back surface of the chip. So what is actually the steady state temperature difference between back and front surface? So here the 4 watt are actually being dissipated in circuit mounted to the back surface of the chip. Okay. What we are actually saying is where the chip is actually attached to the surface, in that region, how much is actually the energy being generated? It is actually the 4 watt. Okay. So that means 4 watt is actually being generated on backside of the chip. Okay. And the sides are actually going to be insulated. Okay. Sides are actually going to be insulated. So there is actually only one way in which heat can be actually dissipated, and which is actually that way, that is actually the top way, because on top the coolant is actually flowing. Okay, so you understand that, you understand the problem. Yeah.
Yes, sir.
Yeah, so this is
Yes,
actually
sir.
what, this is actually what asked. Okay, So whenever we are actually going to get a problem in hand like this, the first you have to do is you have to actually draw a diagram. Then it is actually going to be very easy for you. So you can actually draw a chip and something substrate on that, and you can actually see that sides are actually going to be insulated. And here or here on the back surface, some 4 watt it is actually coming. Okay, on the top the coolant is actually going to be there. Okay. Then you can actually write down what you have to actually see. So what is actually the steady state temperature difference between the back and front surface? From the back surface, which is attached to the substrate, and top surface. So that is actually the question. Okay. Uh, yeah. So if you see the problem here, it is actually this. Okay. So this is actually the problem. Do you know what kind of problem it is actually going to be?
Sir, one dimensional steady state without heat generation.
Yeah, very good, very good. So here we are actually saying it is having some heat that is actually being given over here. So that is actually kind of a what we can actually say some heat flux condition, right? So on the back side, if you actually draw only this chip, okay, so only this chip, we can actually see that. Okay, so this is actually the chip. So over here, it is actually getting a heat flux of 4 watt. Okay, over here, heat is actually being given out, but to H into delta T. Okay, so all the sides are all insulated. So there is actually only one way in which heat can be actually moved. Okay, and heat is actually going to be rejected like this. So what is actually our equation? Therefore, it is actually d square t by dx square, or we can actually say t is equal to c1x, but c1x plus c2. But this profile is actually not asked. So what we are actually asked is actually the temperature difference between uh, top back about temperature difference between back and front surface. Okay. So we know here what is actually going to be, yeah, here it is actually good. Okay. So the temperature on the top surface, yeah, so here you can actually see that uh, so the temperature on the top surface is actually given as Tt. Okay, so temperature on the bottom surface is actually given as T0. So now what we can actually do is we can actually see that first we can actually find what is actually the Q flux. Okay, because uh, we know what is actually the total heat, and we know what is actually the cross section area. So from there you will actually get what is actually the heat transfer. Okay. Uh, yeah. So heat flux, but we actually know that it is equal to minus k dt by dx. So so we know, yeah, dt by dx we actually know. Okay, from here you can actually see that we know what is actually the k, we know what is actually the heat flux from the above equation. From here you can actually see what is actually going to be the uh, dt by dx. Okay, so what should be actually the dt by dx? Okay, so but we know that since it is actually a linear profile. Okay, so since it's actually a linear profile we are actually talking about. Since yeah, in this, yeah, so here there is actually no heat generation, nothing is actually there. So therefore, we can actually write as dt by dx is equal to Tt minus T0 divided by T. T is actually the thickness. How much is the thickness we were saying? It is actually 1 mm, right? Yeah. So 1 mm is actually the thickness. Okay. So therefore, we are actually saying the temperature on the bottom surface is T0 and on top surface is Tt. So we know what is actually the heat flux. We are just directly putting it into the equation. Okay. So therefore, directly we will actually get what is actually the temperature difference, Tt minus T0. Okay. So even without our basic profile and all, we can actually see we could actually get the temperatures. Okay. Yeah. So can we find the actual values in this case? Can somehow we can we actually find the actual values in this case? It is not possible for us to find the actual values. Okay, so in order to find the actual values, we must actually know C1x plus C2. Okay. So for that, to find two conditions, what are actually the two conditions to so that we can actually find the constants. So we can find the constants if we know two boundary conditions. Okay. So for the two boundary condition, one of the boundary condition is that q at x is equal to 0 is equal to 4, and the other
Hello, sir.
condition, yeah, tell me,
Hello, sir.
yeah, can you hear me?
Sir, you are not recording the session, sir.
Yeah, that's
Sir,
why
you are not recording, sir.
yeah, it is tutorial only, so that's why I'm actually not recording. Okay,
Okay, sir.
these
Fine.
are lectures we will actually record. Yeah. Uh, Yeah. So at x is equal to, we actually said that at x is equal to 0, we know what is actually the boundary condition. It is actually forward. Okay. But at x is equal to t on the top surface, we just said t and h and t infinity. We didn't give the values. Okay. So if you want to actually get the actual values of the temperature on top surface and bottom surface, then you will actually get these values in terms of h and t infinity. Okay, so if the h value is actually given as say 4 and t infinity given as say 30 or something, then we could have actually got what is actually the tt and t0. So as long as these boundary condition values are actually not given, we cannot actually find what is actually the numerical values of tt and t0. But we can actually find the dt by dx because at least one boundary condition is actually given. Okay. Yeah. So that is actually the first question. So those who want to note down, should actually note down. I am not going to solve it as it is, as I said. Okay. So second question, which was that? Yeah, this is actually some energy balance and all those things. So what we are actually saying is a solar flux of 700 watt per meter square is incident upon a flat plate solar collector used to heat water. Okay. A flat plate solar collector. So before that, we can just have a look into the or better. We just see. So the area of collector is 3 meter. Yeah, we just have a discussion of this problem. Okay. So this is actually a flat plate solar collector. So in this case, what we are actually doing is here. This is actually the absorber plate. Okay. So heat flux or solar flux will actually comes over here. So it actually passes through the glass cover, okay, and then strike onto the absorber plate. So absorber plate absorbs the heat, and to what it is actually the attached to the water tubes. Okay, water is actually flowing through these water tubes. Okay, so over here we are having our absorber plate. So on bottom there is actually all going to be insulation. So basically the heat flux coming through the glass tube falls on the absorber plate. Absorber plate get heated up. So with the conduction and all, this water tube is actually going to get heated up, and therefore water. So through that again through convection, the water is actually going to get heated. Okay. So that is actually the function of an solar collector. The area of collector is actually given as 3 meters square, and 90% of the solar radiation passes through the cover yeah, 90% of solar radiation passes through the cover glass and is absorbed by the absorber plate. Okay, so out of 700, 90% is actually absorbed. The remaining 10% is actually reflected away from the collector. Water flows through the tube passages on the backside of the absorber plate and is heated from an inlet temperature Ti to an outlet temperature T0. The cover glass, the operating at a temperature of 30 degrees Celsius has an emissivity of 0.94. The cover glass is actually operating at a temperature of 30 degrees Celsius and has an emissivity of 0.94 and experience radiation exchange with the sky at minus 10 degrees Celsius. Okay. So the convection coefficient between the cover glass and the ambient air at 25 degrees Celsius is 10 watt per meter square. So that means some energy is actually being reflected. Uh, some energy is actually being reflected from the cover glass to the ambient, and also some heat is actually flowing over the top, so that some heat is actually again lost to the ambient. So that's what the first question is. Perform an overall energy balance to the collector to obtain an expression for the rate at which useful heat is collected for the unit area of collected and determine the value. Okay. Yeah. So that is actually the first question. And second is calculate the temperature rise of water. And third is the collector efficiency is defined as the ratio of useful heat collected to the rate of which solar energy is incident. What is this value? Okay, so basically an energy balance is actually asked. Energy balance question is actually going to be used. Yeah. So this is actually the question we actually saw. Yeah. So this is actually the question. So here energy is actually coming in. We are actually saying 700 is actually coming in. Out of that, 90% is actually reaching on the observer plate. 10% is actually reflected on it. Okay. So that's what the first question is. Do just an energy balance. Okay. So we know the solar flux is 700 watt per meter square. Okay. So an area collector is actually 3 meters square, and Q absorbed is 90% of solar collector. So energy balance we can actually write as E in minus E out plus E generated is equal to E stored. Okay. So E in we actually know it is actually 90% only, right? So the rest is actually going to be reflected. Okay, so 700 into 0.9, this is actually 630 watt per meter square, and Q out is actually the Q radiated plus Q convected. Okay, so Q radiated, we have the equation sigma epsilon into Ts raised to more 4 minus T infinity raised to 4. Okay, so that means sigma is 5.600 10 raised to minus 8. Emissivity is actually given as 0.94, and this equation is actually for Kelvin scale. Okay, so therefore we have to actually convert it into Kelvin. And therefore, we are actually getting Q radiated as 190 watt per meter square. So there is actually one important thing. Just as I note, what I am actually saying is, so in our conduction equations as well as convection equations, etc., we are always talking about delta T. Okay, so since we are talking about delta T, it doesn't matter whether we are actually using degree Celsius or Kelvin. Okay? Because either of these cases, the differences always comes to same. Okay? So, but in case of radiation, we are actually talking about T raised to 4. Okay, so difference in not the difference raised to 4, it is actually the difference in T raised to 4. Okay? Since the fourth power is actually comes into picture, always you have to actually use this Kelvin scale, because sigma is actually defined based on Kelvin scale. Okay. So MCP delta T, even though we are actually saying Cp is actually given as kilogram or kilojoule per kilogram Kelvin, even though we are actually saying Kelvin, since we are actually using delta T over here, even if we are actually using degree Celsius, it is actually okay. Okay. So that's why that is actually something you have to actually follow, or you have to actually be careful of. Yeah. So next one is actually the heat convected. The heat transfer coefficient is actually given as 10, and the temperature difference we actually said that so we actually said that for radiation also the glass is at 30 degrees and it is actually exchanging its heat with the sky, which is at minus 10 degrees. Okay. For convection, it is actually exchanging heat between the plate at glass at 30 degree and ambient, which is at 25 degrees. Okay. So therefore, we can actually see that the collected useful heat is 630. It has actually absorbed actually. Okay. Out of that, there is actually out of that, this Q E out is actually there, which is actually the loss. Obviously, there is actually no heat generation. Okay, so we have to actually write E in minus E out is equal to E stored. Okay, so therefore 600 minus 194 plus 50. Okay, 194 plus 50 is equal to the energy stored. So that is actually the first question. Okay, so 386 watt per meter square. So you can actually see that out of 700 coming, 700 or 7, yeah, out of 700 coming, only nearly half is actually going to be saved. Okay. Yeah, next question is to find the temperature rise. So that is actually very simple. So you know how much is actually the heat absorbed. So that is actually 386 we have actually absorbed by the plate. And that is actually watt per meter square. And what is actually the total? So into area. Into area. Area is actually given us 3. Okay, so 3 meter square is actually given as area. So therefore, that is actually the total heat absorbed we can actually see. Okay, so that is actually the total heat absorbed, 386 watt per meter square into 3 meters square. So yeah, then using the equations mCp delta T, we know that whatever the energy absorbed is actually used for rise in the temperature of the liquid. Okay. So therefore, directly we can actually get what is actually the temperature rise in the. Okay. And third one, it is actually very simple. It is actually given as useful energy divided by incident energy. The useful energy is 386 divided by 700. Okay, 1 minute. Yeah, sorry for. Yeah, collector efficiency was actually given as useful divided by incident. Useful is 386 divided by 700. So only 55% is actually going to be effective to use. Okay. So therefore, we can actually see that if we can actually reduce the um emissions under. Okay, so if we can actually reduce the losses, then more thing can be actually saved. Okay. Yeah. So that's what we can actually think of. Uh, then next question is actually the next question. Yeah. So find the temperature profile in slab subjected to convective boundary condition on both sides. Yeah. So here you can actually see. So T infinity one, or we actually did maximum boundary condition TS1, okay, or TS1, and one side convective cooling we actually see, but we didn't actually do both sides convective cooling. Okay, that is actually not difficult at all. Okay? I'm not going to solve this, but what you have to actually do is so what you have to do is we know T is equal to T C1. Oh, sorry. Uh, how to rub this? Okay. We know C1x plus C2. Okay. So that is actually the equation. So it is actually nothing but the same thing we have to actually use. Okay. So we have to first put the boundary condition at x is equal to 0. We have to actually put h into T infinity 1 minus Ts1. Okay. Is equal to minus k dt by dx. So what is actually dt by dx? Minus k. What is actually dt by dx? It is actually C1. Yeah. So from here, C1, you will actually directly get C1, which is as where is C1? Yeah. So C1, you will actually get directly from here. Uh, yeah. But the issue is that we don't know what is actually TS1 also. Yeah. So TS1 also what it is, we actually don't know. Okay. Uh, yeah. So that is so therefore it is actually a bit tricky. So what you can actually do is. Uh, yeah. So what you can actually do is you can actually write at x is equal to 0, at x is equal to 0, we know that t is equal to t1 is equal to c2, right? T1 is equal to 0. If you are actually putting into this equation, you will actually get T1 is equal to C2. Okay. So that is actually what we are actually getting directly from the equation. Okay. When you are actually putting the boundary condition, you are actually getting another equation, which is actually written it like this: minus k into yeah, Ts1. Okay. So minus k into C1. So that also you can actually write minus k into Z1 is equal to h into T infinity 1 minus, instead of Ts1, we are actually writing C2. That's it. Okay. So again, at x is equal to L, if you actually write, you will actually get Ts2 is equal to Tc, sorry, Ts2. Okay. So Ts2 is equal to C1 C1L. Okay. Again, sorry. Okay. C1L plus C2 you will actually get. Okay. So therefore, again, at x is equal to 12, that is actually from the equation you are actually getting, right? So what you have to actually write is you have to put the boundary condition. So if you put the boundary condition, then you are actually getting minus k, again C1 is equal to dt by dx, okay, is equal to h into Ts2 minus T infinity 2. Okay. So to this Ts2, you should actually put this equation. Okay. You should actually put this equation. Okay. So then you can actually see that if you're actually taking this as equation 1, and minus k C1 is equal to h into C1L plus C2 minus T infinity 2. Okay. So this is equation 2. So here, if you see equation 1 and equation 2, you have two equations. Okay. And how many unknowns now? How many unknowns are there?
Two.
Two unknowns. Okay. So therefore, you can actually directly solve for C1 and C2. Okay. Yeah. So that's how you can actually calculate this C1 and C2. Once you actually have C1 and C2, you have to simply put it like this. Okay. Yeah. So the interesting thing is that again you can actually find what is actually the Q unknown. Yeah. So I think the temperature profile only asked. Okay. So you can actually find and you can actually put it into that. So interesting thing is that if you are actually asked for a heat flux, then you can actually see that you can actually derive it to the equation T infinity 1 minus T infinity 2 divided by. Do you know what will actually come on the denominator? What will actually come on the denominator? What will actually come in the denominator? Heat flux is equal
So
to R.
R
Yeah.
conduct.
Right. So R conduction. What is actually R conduction? First convection is actually there, right? First
Yes,
convection is
sir.
actually there. So it will be 1 by H1. Okay, since we are actually talking about heat flux, the area not comes into picture. Okay, plus L by K plus 1 by H2. Okay, you can see that this particular equation automatically comes out. Okay, yeah. So that's how you can actually solve this boundary. Yeah, that's how you can actually solve this equation. So it's very interesting. It is actually a bit more involved, but it is actually very simple. Okay. Yeah. So that's how any of the basically that's how any of the equations have to actually solve using the boundary conditions. And it's very tricky from questions to questions. So it might be actually a bit tricky, but you can actually do this. Okay. Yeah. So the next question, a 1 meter long steel plate. Okay, 1 meter long steel plate we are actually talking about is well insulated on its sides while the top surface is at 100 degrees Celsius. So well insulated on its sides means there is no heat transfer in that direction. Okay, so it is actually in here. So therefore, it is actually 1D conduction from that itself. You should actually get. So while top surface is at 100 degrees and bottom surface is convectively cooled by a fluid at 20 degrees Celsius. So 100 degrees Celsius on the top and the bottom is convectively cooled by 20 degrees Celsius. Yeah. So T infinity I is equal to 20 degrees Celsius. Under steady state condition with no heat generation, a thermocouple at midpoint of the plate reveals a temperature of 85 degrees Celsius. Okay. So what is actually the value of convection heat transfer coefficient at the bottom surface? Okay. Yeah. So this is again a 1D conduction only. Okay. We have actually drawn these equations and all. So how we can actually solve this is yeah. First, you have to actually find what is actually the value of convective heat transfer coefficient. So here, what all things we are actually having? We are having T top is equal to 100 degrees Celsius. Okay. T middle is equal to 85 degrees Celsius. Okay. And we know, do we know the distance between these two? Do we know the distance between these two? Okay. The total
Point
is
five.
equal to, yeah, total length is equal to 1 meter. It is actually given. So we can actually call this as D. D is actually given as L by 2 meter. Okay. And it is actually given T infinity I is equal to 20 degrees Celsius. So any idea on how to proceed with this? The conductivity is actually given as 50 watt per meter cube. Okay. So any idea on how to proceed with this?
Sir, we just need to find the Q based on the information, and then like assume it is a series. So the
Assume it is
conduct.
a,
Yes, sir.
assume it is a, I didn't get that.
Yes, sir. This one half of the length we can find the, or we have the information of
Yeah,
temperature differences.
yeah,
So we can
minus
find the Q.
KDC. Yeah, yeah, very good, very good. So that's how we can actually proceed. So from here, we can actually find, I think I have the solution. Let me check if I have the solution for it. Okay, yeah, I have the solution for this. Yeah. So the basic energy balance is actually saying that Q conduction should be equal to Q convection. That is actually the basic energy balance. Okay. So always start with the energy balance, then it is actually going to be easy for you. Okay. So basic energy balance we can actually. For according to this equation, you can see that since there is actually no heat generation, whatever actually conducted in the direction from top to bottom, obviously heat is actually transferring from top to bottom. That same heat should be actually passed over here. You should be actually going to be same. So therefore, as you said, very good. The basic idea is to actually find the heat flux. Q is actually given as K into dt by dx. Okay, Q is actually given as uh, K is actually given as 50. Delta T is 100 minus 85 divided by the half the distance, half the total length. So it is actually given as 1.5 kilowatt. So, but yeah, so now we actually got Q. So, but again, Q is equal to H into uh, A into T S minus T infinity. Right. Okay, TS2 we can actually say T bot. Okay. Yeah. So therefore, uh, yeah. So therefore, it is actually given us, yeah, since we are actually talking about heat flux, there is no need for area. We are talking about heat flux. Uh, so therefore, it should be kilowatt per meter square. It is. The heat flux is equal to T bottom minus T infinity 1. But T bottom also we are not sure. Okay. So we can actually find T bottom again using the same relation. We know what is actually the thermal, the total heat flux. We can actually use two equations where K into 100 minus TB divided by 1 we can actually use. It is actually same as K into 85 minus TB divided by 0.5. Okay, so both we can actually use. Either of these equation you can actually use. So yeah, here it is actually used as 85 minus TS, but you can also use 100 minus TB divided by 1. So if you are actually doing that, either of these equation, you will get what is actually the bottom temperature. Here it is actually given as TS. Bottom temperature you will actually get. So once you actually get the bottom temperature, then everything is easy. Then again we know Q is equal to H into TB minus T infinity I. So we know now what is actually TB. T infinity I is actually given from here. Directly we will get the heat flux, heat transfer coefficient. Okay. Yeah. So it is actually as simple as that. So you have to actually just go for this. Uh, yeah, you have to just go for the energy balance. Okay.
So hello, sir.
Yeah, yeah,
Sir, instead of finding the Q and then again substituting back finding the TS,
yeah.
we can use the that slope formula, sir, that T1 minus T2 by L, which we derived using the in the using the boundary conditions. We can
Yeah,
directly find the temperature at the surface
yeah.
using the slope thing, sir.
Yeah, they're basically same thing. We are actually, yeah, that is true. We can actually find the slope. Yeah, there are actually many methods. You can actually find the slope. But again, you have to use either of these equation to find the heat temperature, right? Not temperature, but to find the heat flux. Heat flux using any of that equation. Yeah, that is true. You can actually directly use the slope, and you can actually do this. That is also done very well. Uh, Yeah. So that's how we can actually find the heat transfer coefficient for the convective cooling. Okay. So that actually, yeah. So these are actually some problems. I think, yeah. So the next two problems are actually from the thermal resistance concept. Okay. So these are actually some problems which we can actually see from the energy balance or 1D conduction. Obviously there are actually if you see in Cropra there are actually so many questions. Okay, so 20, 30, or 40 questions you can actually see in some books it is as, or some chapters it is, or even more than 100 problems are actually there. Okay. So you can actually see just choose some of the equations, some of the problems, and then you can actually try to solve it. Okay. If you have any difficulties, just approach me. So any doubts still here, or the concepts are actually clear? So okay. So now we are actually going to see the next one. So here, the rear window of an automobile is actually defogged by passing warm air over its inner surface. Okay, if the warm air is at 40 degrees Celsius and the corresponding convective coefficient is actually 30 watt per meter square Kelvin, what are the inner and outer surface temperatures of 4 thick window glass? Okay, if the outside ambient temperature is 10 degrees Celsius and associated convective uh, coefficient is 65 degrees Celsius. Okay, yeah. Here you can actually see that we are having an automobile window. Okay, so what we are actually saying is on one side we are actually having 30 and 40 degrees Celsius. On other side, we are actually going to have, okay, other side we are actually going to have 10 degrees Celsius and 65 watt per meter square Kelvin. And the thickness is actually given as 4 and conductivity is actually given as 1.4 watt per meter Kelvin. So what is actually asked? We need to find what is actually the temperature surface T1 as well as T2. So since we have already solved this temperature profile over here, you can directly take from that and you can actually do this. Okay, so we have already know what is actually the temperature profile, or we have already solved this equation. Okay, so the same condition we have actually solved now. So we have to actually put at x is equal to 0 what is actually the value coming. So you know all the boundary conditions, right? So you know all the boundary conditions. So your t is actually going to be, so over here t is actually going to be a function of x, L, H1, T infinity 1, and H2 and T infinity. Okay? When you actually derive your equation, you can actually see that. So everything is actually known. At x is equal to on inner side, we can actually put x is equal to 0. And if you are actually putting x is equal to 0, then at that point you have to actually put appropriately take T infinity 1 and Th2. That's it. Okay. And the outer side you can actually put x is equal to L. Okay. So in that case, you can directly find what is actually the temperature surface on both sides. Okay. So that is actually the one method to do that. Yeah. So that is actually since we already solved this equation, that is actually the best way to do this. Okay? Otherwise, what you can actually go for is actually the electrical resistance analogy. Okay? So electric resistance analogy, you can actually see. So here it is actually given as 40 degree, and outside it is actually given as 10. And the first one, H by 1 by HA. Okay? So L by KA, again 1 by H2A. Okay? 1 by H1 over here and H2 over there. Okay. So yeah. So from here you can actually find what is actually the total heat. So since we are actually the cross-sectional areas are actually not given, so therefore we can actually calculate heat flux. Okay. So instead of HA, you can actually simply calculate H itself. So from there you can actually calculate what is actually the Q. Once you actually get the Q, then how we can actually find? Okay, once we actually got the Q, then you can actually use the equation H into T infinity 1 minus Ts1. Okay, so from there, first you are actually using the whole circuit. First you are actually using the whole circuit to find the heat flux. Okay, then you are actually using a, so this is actually Ts1. Okay, and this is actually Ts2. Okay, so first we are actually using the wall circuit, wall potential to find the total heat flux QW. Then you are actually using the partial ones. Okay, so now we actually know what is actually the heat flux. Now the question is actually the Ts. Okay, so therefore you can actually write thus 40 minus Ts1 divided by 1 by H, or 1 by H. Okay. So which is basically equal to, which is actually basically equal to H into T infinity 1 minus Ts1. Basically the same thing. Okay. So just from electrical resistance point of view, we are actually seeing. So we know what is actually the heat flux now. We know the H also, it is actually known. H is actually given as 30. So from there, you can directly calculate what is actually the Ts2. Okay. How can you actually calculate Ts2? How many ways in which we can actually calculate Ts2? Just tell me. How many ways we can actually calculate Ts2? Okay. First method is, okay. First method is we can actually calculate first two resistance. Okay, so we can actually calculate from T infinity 1, Ts1, Ts2. So you know what is actually the 1 by H and L by K. Okay, so using this circuit, you can actually solve what is actually Ts2 because everything is actually known. H is actually known, L is actually known, K is actually known, T infinity 1 is actually known, and obviously the Q is also known. Second one is we are actually assuming only the other part. Okay, so Ts2 and T infinity 2, 1 by H2A. Okay, so here also we actually know Q. So we know Q. So only unknown is Ts2. H2 also we actually know. So T infinity 2 is also we actually know. And so that's how we can actually calculate. Can anyone say a third method in which we can actually find this Ts2? Anyone dare to attempt?
Middle resistance.
Yeah, very good. So we can just use the middle resistance itself, Ts1 and Ts2, because we already know Ts1. That's why. So first we actually calculated Ts1, so therefore we can actually use this one. Okay, if we don't know or we haven't calculated Ts1, this cannot be actually done. Since we already calculated Ts1, we can actually use it. Okay. Yeah. So this way you can also calculate Ts1 as well as Ts2. So that is actually the question, right? So what are the inner and outer surface temperatures? Yeah. Okay. So likewise, what you have to do is you have to first draw a diagram. Okay. First draw the diagram. So then you will actually get the better idea of what are actually the things need to be done. So then write down what are actually the known quantities, and then write down what is actually that you have to actually find. Okay, so that is actually the way in which you should actually proceed. So if you're actually doing like that, then it is actually very easy for you to get the. It is actually easy for you to understand the problem. Okay, so the last one, it is again the this thermoresistant solid. A composite wall of an oven consists of three materials, two of which are actually of non-thermal conductivity Ka 20 and Kc 50, and non-thickness La and Lc. Okay. The third material B, which is sandwiched between material A and C, is of unknown thickness 0.15 meter. But it is of non-thickness but unknown thermal conductivity. Under steady state operating conditions, measurement reveals an outer surface temperature of 20 degrees and an inner surface temperature of 600 degrees Celsius. Okay, and an oven air temperature of 800 degrees Celsius. The inside convection coefficient H is known to be 25 watt per meter square. What is actually the value of Kb? So first we can actually draw. This is actually the composite wall as they are actually saying. So it consists of three materials, okay, A, B, and C. Okay. The thickness are all known, La, Lb, and Lc. So thickness are all known. The conductivity of Ka is also known. Kb is actually unknown. Okay, unknown, and Kc is actually known. And on the other side, one more thing is actually known, which is equal to H and T infinity. Okay. So the temperature, yeah. So the temperature steady state condition operation measurements release that outer surface temperature TSO. Okay. So that is actually the surface temperature on the material as outer surface temperature. It is actually given as 20 degrees Celsius, and inner surface temperature. Inner surface temperature is actually given as 600 degrees Celsius. Okay, 600 degrees Celsius. So that is also given. Okay. So only unknown is Kb. That is actually the only unknown. So how can we actually proceed? How can you actually proceed? Because you have to actually obviously draw this.
Sir, first we need to find the Q for convection. All the data have been given for convection.
Yes, yes, yes. Yeah. So that
And
is actually, yeah.
yes,
Yeah. So first we can actually find Q from H into dt by H into delta T, which is actually T infinity minus Ts. You can actually find, right? Then from there we can actually find what is actually the temperature at this point. Okay, say T1 and T2. Okay? We can actually find what is actually the temperature at this point if you want. Right? You can actually find the temperature at this point using Q again is equal to K into T1 minus Ts1 divided by L is actually given. Okay. Again, T2. Uh, can we actually find T2 here? K into T2 minus T1 divided by LA. So here Ka, Kb into Lb. Can we actually find the T2 over here? Is it possible? It is actually difficult because we are actually not having, we don't know what is actually Kb. Okay, yeah. So it is actually a good start. What you actually said, it's actually a good start, but we are actually stuck in between. Obviously, we can actually do this in this way, but the easiest way is actually go for the thermal resistance. Okay, yeah. Obviously, what you actually said is actually true only, you can actually do that. A bit more involved it is actually going to be. You can actually write Q is equal to Kc into T2 minus Ts divided by L. Okay. From here you can actually calculate T2. Okay. So, but here from this equation you can actually calculate it. So here Ts0, right? Ts0. So T2 minus Ts0 divided by LC, you can actually calculate T2. Okay. So once you know T1 and T2, you have to actually put again back into the equation. Only unknown is actually the Kb. You got that technique? You understood that?
Yes, sir. Getting.
Yeah. So that is actually one way. The other way is directly put it into the thermal. Whatever we actually did is actually the thermal resistance only, but in a different manner. So the other technique is actually put into this thermal resistance. Okay. Yeah. So as you said, since there is actually one unknown, so first we have to anyway calculate this heat flux. Okay. So therefore, we are having the circuit. So first we are actually taking first one, first circuit, which actually says Q is equal to T infinity minus Tsi divided by 1 by H. So that is equal to H into T infinity minus Tsi. Okay. So that actually gives us the Q. Okay. And again, you can actually use the circuit again, either the wall circuit, either you can actually use the wall circuit, or you can actually use the part of the circuit. Either of the way, you know Q is equal to say Tsi minus Tso divided by La by Ka plus Lb by Kb plus Lc by Kc. So only unknown is actually the Kb. So from there also you can actually do this. Okay. I think yeah. So the same way you can actually do this. Okay, yeah. So basically the same thing only, but it is actually a bit involved from the physical point of view, physics point of view. Here we are actually directly using the technique of thermal systems.
Excuse me, sir.
Yeah, yeah.
Sir, if the question is asked like which is the better arrangement, like an additional question, sir.
Yeah,
Which
okay,
is
yeah.
the better arrangement, sir? A, B, C, or CAB? What would be our CBA? What would be our answer, sir, at that time?
Mm, so there is actually two ways in which obviously the heat flux will not be actually changed in that case. Yeah, but
Yes, sir. Heat flux won't be changing, but if someone asks like what which is the better way of conducting heat, like it will be effective heat.
uh,
So, say,
so what
like
you
what
have
will
to, yeah, what you have to do is in that case. So people might be actually asking what should be actually this TSR, but I don't think it will actually vary because this is actually a resistance, series resistance. So therefore, I don't think whether it is actually coming over here or it is actually coming over here. I don't think it is actually varying because just it is actually summation here on there, right? Whether it is actually coming over here or coming over there, both might be actually same. Okay. So if you have any objection, please let me know. So that is what I am actually getting from if you're actually asking like this, right? We are actually doing it like over here, or if you're actually summing it over here, uh, yeah, it is simply that the summation instead of LB by KB over here, it actually comes over here, right? So that's what it is actually going to. This difference will come. Difference will come when you are actually talking about the cylindrical. Okay, so there the difference is actually comes into picture. That's what we will actually see the next section. Okay, so difference come because over here, if we are having say some fluid is actually flowing inside. Okay, some fluid is actually flowing inside say T infinity one, and you are having two material. Okay, so you are having two material. So here you can actually see that even though it is actually in series, the cross section area is actually increasing. Okay, for example, material A and material B we are talking about. Okay, so material A it is having some amount of cross section area. Material B it is having some other area. Okay, so this here we all cancelled the areas because everywhere the area is actually same, right? So therefore, it actually doesn't matter. whether it is actually comes into picture. But if this is actually the case, then you can actually see that if you are actually keeping LB over here or material as a B material inside, then we are actually multiplying with some area A1. Whether we are actually multiplying the material C with some area A2. But if we are actually having the interchange, then the multiplication actually comes into picture. Okay, so in that case, it actually matters whether it is actually coming inside or outside. For this composite wall, for a 1D Cartesian system, that actually not going to matter. Okay, yeah. So this one, it is actually this thing. It is actually going to matter. So whether it is actually comes inside or outside. Yeah. So very good question you actually asked. Maybe we can actually see one problem from there. I'm actually not sure, but see while teaching, it actually comes up or not. Okay. Okay, so that's actually about our tutorials from 5-6 problems. Okay, so you should actually go through many more problems. Okay, as much problems are as you can, so you'll get the better ideas. Okay, so in exams, so 90%, more than 90% itself will actually come from problems. 90%, or if not 100%, are actually from problems. With derivations, etc., is nothing much to us, especially since it is actually open, not open internet exam we are actually talking about. Okay, and open WhatsApp exam we are talking about. Okay, okay then. So is it clear?
Yes, sir.
Yes, sir.
Yeah. So then we can actually stop over here if you are not having any doubts. Okay. So then we can actually meet on Monday. So tomorrow, since we have taken 1.5 hour session this week, so we can actually skip the class for tomorrow. So we can meet on Monday. Okay. Yeah. Then have a nice day to all.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.